Okay, so this is about um, lately I was trying to get in, just see what Tephra correlation is like geochemically a bit, because I felt inadequate in that way. So I asked Solin to do some probe work, and then we also wanted to look at, well, are there some statistical techniques that aren't out there too much yet that we could look at and see if they can help us to think about what's going on with some of these tephra layers. So she actually did go to University of Edinburgh and use a microprobe there, and so insofar as possible, I became a geochemist. No, that's not going to happen. So I'll talk. This is mostly about the statistical techniques applied to the data, to geochemical data. I'll talk a little bit about location, then traditional comparisons for the data set that we have, then principal component analysis and the results from that study, and then again talk a little bit about thickness in terms of something that's useful to always get from tephra layers, if it's possible. That and the grain size, and I'd like to keep bringing that up. Then another technique called clustering, and then talk about a model of deposition for this site. So the location is Bernie Spring Mountain in Northern California, just a bit north of Lassen Peak, right there, and so it's in amongst all these wonderful tephra sources in this region. And there they are again in another view, a lot of these ones that Sean just talked about. So we can use we should use a lot of techniques to correlate, insofar as possible, geochemistry, age, and lithostratigraphic characteristics, and I think we can think of that in a whole unified framework, really. In terms of the geochemical techniques, the traditional techniques involve making binary plots, and the work that we did, we tended to go for these element oxide ratios in the binary plots, based on suggestions of the petrologist or real geochemist that we were working with, Joaquin Cortez. So these are all, this is SiO2 over Na2O and K2O over Na2O, et cetera, on these other plots, showing the comparison of the tephra layer of interest, which is the black dots, against the targets that we're shooting for. A lot of insofar as possible, the targets were also analyzed on the Edinburgh machine, using the same techniques that we used. That's not always the case, though, so there's limitations in doing this always. Using binary plots, it's difficult to compare quantitatively no matter what, but also these plots also have a little bit of this problem with the different instruments and different labs and things like that are big problems. But insofar as possible, we tried to standardize on that. You can get some idea of how spread out the data were from the unknown that we had. It's kind of all over the map, although they do seem to cluster a little bit tightly in the data do seem to cluster a little bit tightly in certain areas on the graph. So this was one big problem with this tephra layer, is that the distribution of the data points is actually quite widespread relative to the targets. So using the standard similarity coefficient, the unknown didn't really match much of anything very well. None of these would have been acceptable. The highest match that we got with the similarity coefficient was about 0.87 with the Rockland tephra, which is actually about the right age for this deposit. So that's kind of lucky, but that we can only use that as a guide then, that it is possibly the best match, but we got to keep thinking of these other Tephras. So that kind of brings up one of the things that we've all known for a long time about the similarity coefficient is that it's difficult to get an idea of the error in that, but it's a good guide for sort of looking what sort of age range or what sort of tephras to look at as possible targets. So what we, in the first experiment that I asked Solène to do, I asked her to use principal component analysis. And the thing about principal component analysis is that it basically reprojects the data, and in this case that's the chemical compositions, reprojects the data onto axes so that you can see the axes that have the maximum variance in the data on them. So the axis that has the most variance, shows the most variance in the data, is principal component 1, and then the second to the most variance is principal component 2, and then down the line until these higher order principal components have very little of a variance in the data. So it allows you to look at the data so that it's as spread out as possible in terms of discriminating between the different data sets. Even so, you can see it's still quite a jumble on there. And we could have done something like the kernel function technique, one of the kernel function techniques that Ryan talked about the other day. That might have been helpful for us to put levels of confidence on this. But what Solène decided to do is look at the error ellipses on here. These are 95% confidence limits on the different samples. Again, the unknown is the black oval there. So she decided it might be possible to discriminate a little bit better if you take out the outliers, because again the unknown was quite variable in composition. So she took out the outliers, which are the ones outside of the error ellipses on this case, and redrew new 95% error ellipses, and it did help us get a little bit more confidence that actually maybe the Rockland is the right correlative target for this unknown. So this is the 95% confidence ellipse on the reduced data set, and looking at that, it is suggesting that the Rockland composition is sort of at the core of that error ellipse, and that therefore it might be the best match for this tephra. We sent a split of the sample to Elmira Wan and asked her to take a look at it. And although that wasn't the Rockland was not the tephra that came up with the highest similarity coefficient on it, it was pretty high. So that gave us a little bit more confidence that maybe the Rockland tephra is the best match target-wise. This tool, just like the similarity coefficient, although you can actually get quantitative limits to your uncertainty on the principal components, just like similarity coefficient, it's not something that we can use indiscriminately and alone as a tool to just decide this is what's going on. We always need to consider the context and all these other factors to make sure that that's the best match. So as far as we can tell, that might be about the best match in this case, but it's something worth, God bless you, something worth to keep thinking about. These statistical techniques should be used as guidelines, not as the ends-all and answer, even if they are pretty sophisticated techniques like principal components. If we accept that as the correlative, the Rockland is actually found at a number of sites in the American West, and the blue dots on the map here show these sites where it's found, California and Oregon right here, and what she did next was plotted up the thicknesses that have been found at these different sites, as well as the site that she was working at, to see if they make sense relative to this thickness drop-off of an exponential thickness drop-off with the square root of area encompassed by a thickness isopack. And strangely enough, although this Rockland tephra is about 600,000 years old, and so you would expect some quite a degree of redeposition in it, the thicknesses that you get within these different isopacks are all actually consistent with the area that's encompassed. For example, the points that are closest to the vent here on this would be the downwind side toward the southwest. These all have quite large thicknesses close to the vent here, around a meter or half a meter. And then the points in this isopack, many of them, even offshore sites, are around 30 centimeters or half a meter. So the thicknesses are consistent with the typical drop-off in thickness that we expect as volcanologists. This is despite the fact that a lot of these sites don't have detailed descriptions of the internal stratigraphy of the layers at those sites. So we have no idea whether how much was clearly redeposited or how much was clearly primary at the different sites. But you can actually make isopacks that make sense out of this. If you do that, Andre had an old, I think it was in an older paper that you had an estimate of the volume, about 50 cubic kilometers. This volume that you get is about 200 cubic kilometers if you add that all up, which I would think is somewhat unrealistic, to be honest with you. But nevertheless, it is internally, the data set is internally consistent. Okay. So from the point of view of the geochemistry and the point of view of the thickness measurements, it kind of makes sense. I'm not going to go into that. Clustering. Just like principal component analysis tries to allow you to look at the maximum variance within the data set you have, clustering is another technique that's trying to optimize some view into the data set that you have. And the idea behind clustering, if you can think of the geochemical analyses as clouds of information in a compositional space, clustering is a technique, depending on how you set it up, it lets you look at those clouds in different ways. So the clustering technique we did was a technique to define the number of clouds and the sizes of clouds of these geochemical analyses in multidimensional compositional space, so that the distances between the clouds were maximized, and the distances between the analysis points within the clouds was minimized. So trying to both get the most compact clouds and the biggest distance between the clouds. We used an unsupervised, a number of unsupervised techniques and fused those different measurements. Unsupervised means that we actually didn't give it any predefined idea of what data should actually go together. So we didn't tell it that, okay, all these analyses of Bishop Ash should actually go together. There was no information given to it like that. It was just completely done without any intervention from an intelligent operator. If you do that, you get some kind of interesting looking results. And the different colors just mean different clusters. So there's about 5 clusters that you get as far as trying to optimize these distances. Notice that a number of so these are your typical, here's the unknown of interest. Here's another unknown that we had, Bishop Ash, Huckleberry Ridge, Lolita, Lava Creek, Mazama, a lot of the typical widespread ashes that you get in the region. Okay, one thing you'll notice is that a number of the ash layers, they're 100% within one cluster. So they are all clustered well. They're all close together. Oddly enough, a lot of them are in the same cluster, though. So Bishop Ash and Huckleberry Ridge, Lava Creek are all within one cluster. Again, just in terms of optimizing it in terms of this mathematical measure of distance. Rio Del, Trago, and Wono are also all in one cluster, as well as Mazama. Okay, so it can't necessarily discriminate among ash beds, but it does tell whether certain ash beds are really one ash bed. And I think that's what these ones mean that are all at about 100%. Now, there's a few of them, though, where the number of the samples are distributed into various clusters. Primarily are unknowns, but also notice the mono ashes and Mount St. Helens ashes are in multiple clusters, more than others. With mono, this is from all of the layers of the Wilson Creek Formation that we talked about before, and there actually is some chemical variation in those layers. So we think that's reflecting that, that variation. And then for Mount St. Helens, this is actually several of the different Mount St. Helens layers that are analyzed in that. So there actually are separate ash layers in these two, unlike these monolithic ones. And then for the unknowns, this seems to be indicating that there's different components in there. And then in checking against Elmira's results, she said that, in fact, she did find shards from several different eruptions within these two unknowns. So this seemed to be helping us as a guide to whether there was some mixture of shards within the samples. So the basic idea that we had for how this deposition might work in this situation, the place where these samples were found was a hill slope hollow, or a hill slope basin. So the side of a small volcano, a very small basin on the side of the volcano, maybe about 100 meters by 300, 400 meters long. And we think that what might have happened here is that ash fell on the surface in these different eruptions and was blown into the receiving basin here. We actually have good isopac data that show that the ashes are concentrated in the basin area here. But at the same time that the youngest ash was mobilized, anything that was a little bit older than that youngest ash, the main primary component of the youngest ash, was actually mobilized into the basin at the same time. So the process was able to pick up glass shards and preferentially move them into the basin, whether they had fallen on the surface very recently or within the past 20,000 years or so. That's the best explanation we can come up with. It's kind of a very enigmatic environment. It seems to be wind-driven. As far as moving the material into the basin, there's a loessy layer underneath these ash layers. So it's a wind-driven system that preferentially picks up glass shards and puts them into this lower receiving basin. And I was talking to Andre earlier about this because I couldn't understand why it would just pick up glass shards preferentially, and he reminded me that these things are aerodynamically able to be picked up very easily. Their density is low, and plus they have very aerodynamically erodible shapes. So it's possible that the tephra gets picked up preferentially because of its low density and aerodynamic shape. Okay, so the statistical methods can be used to help us understand the tephras and get a better idea, gain a little bit of confidence in matching, and we can put some numbers on our confidence. 95% confidence level seemed to work for us with some caveats. Problems with these techniques are that the chemistry between two different layers might be very similar, even though we actually know that they're different layers because we used unsupervised techniques. There do seem to be other layers, though, that are characterized by at least two different types of geochemical signals. And if you've got questions for more details, this is Solen's email address, and you could email her there. Thank you very much.
Yeah, okay. I figured there'd be a few comments. I think it should be live already.
Hello, am I live? All right, barely. I have some questions about what variables were used. Were the 9 usual oxides that?
Yeah.
All
Gosh. Sorry.
All 9 were used.
Yeah, that's right. For that, we actually did different experiments with taking some out, and so you do get a different result if you do take some out. You know, if we're worried about sodium,
yes.
So we tried taking that out and seeing what that would do. So it does depend on what chemicals you actually keep in there.
It definitely does. Not only that, but depending on what volcanic province you're dealing with, certain oxides will be more dependable. For example, magnesium oxide will be higher from, let's say, the Cascades, whereas if you go to the monocraters or to the Bishop, it's at close to detection limits. So if you stick magnesium oxide or manganese or something in there, you're going to just put a whole lot of scatter and error into that.
Exactly, yeah. So we tried to be as sensitive to that as we could and do different experiments with keeping different oxides in and taking some out, as well as doing the experiments with the ratios instead of the oxides themselves. So no matter what you do always get this phenomenon that some are completely homogeneous no matter how you break it down, and then some are always mixed no matter what you do. And globally, it wasn't sensitive to that, but certainly the particulars varied from one analysis to another.
Which cluster analysis did you use? Any particular version?
Wait, I'm sorry, Andre.
Which cluster analysis? There are several different kinds.
Yeah, we didn't use a canned program. We actually built that technique from scratch, working with a mathematician. Yeah. It's actually using several different cluster classifiers and fusing the results from the several different classifiers. So.
Well, there is a cluster analysis that's been around for a long time. It's called Parkes Cluster Analysis, 1970, and I've used that and gotten good results. But you have to a priori plug in those variables which you consider to be the most precise for that particular province. Yeah. If you compare very different provinces, you wind up having artifacts that compare apples and oranges and say that they're the same. So
yeah. And we didn't want to do that. That's why we did numerous experiments and then didn't use a canned program, so we had complete control over the mathematical superstructure.
The problem is you have an unknown and you think it's Rockland, okay? That's the basic problem. I say that the problem is you have an unknown Tephra and you think it's Rockland because you ran it through the similarity coefficients and you've gone through various other routines that suggest you might be correct. Yeah. But my approach on this would be, okay, I have this sample. Let's see if it's Rockland. So I take a type Rockland sample, something that Andre was mentioning earlier, and I take the unknown, I do probe analysis on it, analyzing at least 30 shards. Then I do the same in the same batch, so there's no calibration differences with the type sample of Rockland. Yeah. And if they are equivalent, then you can see it on these graphical bivariate plots. I mean, it's black and white. Yeah. You've got to have the compositional space has to be coincident with both samples, no matter what sort of element you're using. If you've got traces, even better. But I'm not advocating we don't use statistical methods. They are important. Yeah. But I would say the first approach would be the graphical approach, where you've analyzed adequate data so you can make reasonable decisions about equivalence or not. Yeah. And then if you're still stuck, maybe these techniques that you described would be very useful.
Yeah, I absolutely agree with that, and I think it's the same as with the similarity coefficient. This is a starting point for what you should do, and the advantage of it is in terms of the mathematics is you do get some confidence level on which one is better and which one's worse. So I think there are some advantages to using these statistical techniques when you're starting out. Yeah.
Yeah. Let's see.
Testing different statistical techniques.
I'll throw something in real quick before we've got like 12 people. I think it went. Yeah, there is I think there were signs that maybe you had mixtures of things. That certainly complicates it. And if you can, sometimes, I don't know, I guess you could try the component analysis just on that cloud of data from that one sample, exclusive of everything else, and just see what happens, or just plot it to death and see if you kind of start separating things, and thinking about what proper geochemical trends ought to look like, petrogenetically, and if this goes, if normal trends go one way and you have data going, separated in the opposite direction, they can't really be related to each other, and so pull those out. And then, of course, sometimes unknowns are just permanently unknowns.
So I have to disagree with you, John. I'm sorry. I think that if you graph it up, it seems like no one can sit there and, let's say you have an entire major element and trace element suite, to sit there and look at 80 a matrix of I don't know 15 by 15 matrix to try to see if in every single one of those you are nearby to one another. That seems difficult and also is not quantitative. And so I think that these statistical methods are able to reduce that 15 by 15 matrix down to something that's easier, which then you can look at the graph and see if they're similar. Also, another comment: the principal component analysis I think is a useful beginning because it allows you to graph it, but you can't actually quantify. You still can't quite quantify how similar these little clusters are. A better method is called discriminant function analysis, and if anyone's curious about that, you don't like discriminant function? Oh, it's glorious.
You have to know your knowns, though. It's going to classify to something.
So you have to.
You don't have.
Right, you create a reference set, but by using whatever you choose, like similarity
But you
coefficient.
have to know that it has to come from one of those. Otherwise, it will classify as that, even if it doesn't come from there.
Yeah.
Right.
So it'll put it in one of those bins, even if it doesn't come from there.
But it gives you the Mahabolius distance that you can use to figure out whether it is actually statistically correlated.
I had this problem where I put something that graphically would plot like way over here, and it insisted that it was 0.99 percent probability. Because it's an assumption built into the method that everything shall fit in one of those categories no matter what. Yeah, but if you have that sort of to watch for that, you can double check. Something that I'd love to be able to do is like run one of these principal component things and have it tell me what the that linear equation is that it's using to, and then put and then once you have that for a suite of things, just put that equation into Excel.
Yeah, you can
and just
build on the PCA.
These are great.
Yeah, I don't know enough about principal component analysis to know if this is even a sensible question, but is there a way of factoring in analytical uncertainty into principal component analysis? And do you do that?
Yeah, you could do that. It wasn't factored into these exercises that we did, though, that I just showed. Yeah, it can definitely be done. Oh, one thing I wanted to say is, again, these were two totally unsupervised techniques, so they were yielding results based on. If you want to think of the analog situation that I was thinking about that would be of interest, say you go into a volcanic province where nobody's ever been before, you've never been, so you're collecting the first data set. That's where I think these unsupervised techniques could maybe help you the most, is because, first of all, with principal components, you're breaking the data into the components that have the biggest variance in them, so you're still looking at binary plots, but you spread the data out as much as you possibly can, so you have the best chance of actually finding the different pieces of data. So I think that's sort of the idea of where I think this kind of technique might be the best, is a more completely unknown province.
So Marcus, this looks like the work that Solène submitted to Quaternary Research.
Yeah.
And I was the associate editor on this paper.
Yes, thank you.
And I was struck by the photographs in the paper, and the tephra looked kind of dirty. And if your model is right that it was blown in or somehow washed into that depression at some time after the fact, you're sort of in tephra central right there in that part of the world. And so I guess the a priori assumption is if it is reworked, it may be reworked with some other things which would give you that spread, which is why it was didn't have a very high similarity coefficient.
Yeah. I guess the reason why it's hard for me to understand how that would work is because when you look at the modern surface, you don't see glass all over the surface, despite the fact that you're in basically a tephra hole there, where just everything has to blow into that area. So that's why that struck me as odd that you could actually wash in tephras that might have been sitting there for 20, 30,000 years together with this other one that.
Yeah.
So,
Yeah.
But if you went out and picked up if you went on the hillside above that site, picked up a handful of dirt and cleaned it out, there would be lots of shards in there of mixed affinities.
You're right. You're probably right. And it would be interesting to do an experiment where you just blow air over that surface and see what comes out of that.
Yeah.
It's preferentially glass shards.
So one thing I've run into, we all run into probably these mixed samples, and anytime I have a sample that looks like it has a jumble of stuff in it, I'll actually do database searches on every single individual analysis point. And sort of see what kinds of affinities start coming out, and as a way of trying to figure out how to group these things and what might be related and what might be not, and so essentially putting into I guess you could put them into your principal components and have it treat each shard as if it was a separate sample.
Sure.
I was just wondering, in your principal component analysis, did you look at which oxides dominated your components?
No, we haven't had a chance to do that kind of thing yet.
Okay.
Yeah. With the principal component analysis, you can not only find out how much of the variance is in each one of the components, but you can also find out what one of the original primitive variables went mostly into that component. So yeah, we haven't done those details yet.
Yeah, because I was just wondering, maybe it would be helpful to normalize the data sets before running the principal component analysis if you have some oxides that dominate it wildly because there are more of them in the analysis.
Yeah, we've actually done it both ways, non-normalized and normalized. Yeah.
Okay.
So it's very experimental. So.
One more comment about crypto tephra in the West. All you crypto tephra chronologists don't come out here, because anywhere you go, any stratigraphic section, pick up a handful of dirt and you're going to have shards in it. You look hard enough, there'll be lots of shards. So there's a lot of tephra out here. Whereas out, back east or whatever, it's a rarity, and you're going to get these nice compositional peaks, and it's just wonderful, the stuff that we've been seeing, and it's something that we've dreamed about, John and I, but didn't think it was possible, and it's just wonderful that you're actually picking up all these things way downwind, and it is truly becoming a global technique, and it's wonderful. But out here, it's tough, and you probably don't want to work with mixed systems because we have already enough problems discriminating between individual tephra layers.
Yeah. One thing about I don't know if I made it clear, but these were actually the visible tephra layers. These weren't cryptotephras.
Yeah.